Welcome to Mr. Chalk's Revision Tips. In this video, we will look at the left-hand rule, the motor effect, and electric motors. So, if we're looking at using Fleming's left-hand rule to remember the direction of the motion in an electric motor, it is shown in the diagram to the right. So, the first finger points in the direction of the magnetic field. The second finger points in the direction of the current, and this is a right angle to the field. And the thumb points in the direction of the motion of the wire. The magnetic field can be visualized as magnetic field lines. So the field strength corresponds to the density of the field lines. The total number of magnetic field lines penetrating in an area is called its magnetic flux. A current carrying wire or a coil can exert a force on a permanent magnet. This is called the motor effect, so the wire could also exert a force on another nearby current carrying wire or a coil. So the carrying wire is placed into a magnetic field, right, so whose lines of force are at right angles to the wire. Then it will experience a force at right angles to both the current direction and the magnetic field, which would cause it to move. So the diagram shows an apparatus used to show this. Right, so X is the wire carrying the current. So we're describing what happens to the wire when a current is switched on. So it's going to move because it experiences a force. And if we're looking at what happens to the movement as the current is increased, the movement also increases. And finally, what would happen to the direction of movement if the magnetic field was decreased or reversed, then the movement would be in the opposite direction. Electric motors transfer electrical energy into kinetic energy. So a simple electric motor can be built using a coil of wire. This is free to rotate between two opposite magnetic poles. When an electric current flows through the coil experiences a force and moves. So the direction of the current must be reversed every half a turn, otherwise the coil would come to a halt. This is achieved by using a conducting ring split in two called a split ring commutator. A coil of wire is then used with lots of turns to increase the effect of the magnetic field. So the diagram shows a simple electric motor with only one coil, with the arrowhead showing the direction of the current and the other arrow showing the direction of the movement of that coil of wire. So if we look at the stages of what happens in an electric motor, so the current in the left-hand part of the coil causes a downward force, and the current in the right-hand part of the coil causes an upward force. So the coil rotates anti-clockwise because the forces that have been previously described. So when the coil is vertical, it moves parallel to the magnetic field, producing no force. So this would tend to make the motor come to a stop. But there are two features which allow the coil to continue rotating. The momentum of the motor carries it round a little bit more. So the split ring commutator changes the current direction every half a turn. So once the conducting brushes reconnect with the commutator after half a turn, the current flows in the opposite direction through the wire in the coil. So each side of the coil is now near the opposite magnetic pole. So therefore, that would mean that the motor or the motor effect forces the coil to continue rotating. So the diagram below shows a simple electric motor. So there is a current in the coil, so the coil rotates continuously. If we're explaining why, the key things to talk about are that the sides of the coil experience force. The forces cause moments that act in the same direction. The moments cause the coil to rotate. So the two halves of the rotating commutator swap from one brush to another, so the commutator reverses the current, keeping the forces in the same direction, so keeping the coil rotating.
Thanks for watching.